Okay, let's get started with problem 2.3 from Wald's General Relativity. We'll start with part A here, where he asks us to verify that the commutator satisfies the linearity and Leibniz properties and hence defines a vector field. So just to remind you guys, the commutator of alpha and beta, for example, is just alpha beta minus beta alpha. So if these are constants, obviously this would be 0, but the order of operations matters for things like vectors and tensors. So this is not always 0. Okay, so we can go ahead and check the linearity property. And we start by doing this. We apply the commutator of two vector fields, v and w, to this alpha f plus beta g, where alpha and beta are constants, and f and g are functions. Okay. This equals vw acting on the brackets minus wv acting on the brackets. Okay, now this is going to equal v of alpha w acting on f, so the vector is going to pass right through the constant, obviously, plus beta of w acting on g, close the bracket, minus w, alpha v acting on f, plus beta v acting on g. So now at this point, excuse me, at this point we're free to collect the alpha terms, so we can go like this, because alpha can just be pulled all the way out of those terms. So let's say alpha, this first one is going to be v acting on w acting on f, and then we're going to have minus w acting on v acting on f, and then we can grab the beta terms as well. So we're going to have v acting on w acting on g minus w acting on v acting on g. So with this, it's pretty straightforward. We can rewrite this as alpha times the commutator of v w acting on f plus beta times the commutator of v w acting on g. And this is the linearity condition, so we've shown it. Okay, so we can go on and show Leibniz as well now, which is like the product rule. So we can start with the commutator of two vector fields, v and w again, and let this act on the product of f and g. So this is going to give us vw times fg minus wv times fg. Now we'll apply the product rule. So this is v times, let's do it this way, I think, w acting on f times g plus f times w acting on g. That's how we'll write it. Minus w. Again, we do the product rule here. So this is going to be v acting on f times g plus f times v acting on g. Again, we can just keep expanding here. So we're going to get two terms from this term. We're going to get v acting on w acting on f times g. We're also going to get w acting on f times v acting on g. We're going to get from this next term, let's see, let's do it this way, plus v f w g plus f v w acting on g, and then we get the negative, so the minus sign, can have WV acting on F times G. We can also have V acting on F, W acting on G. We can have W acting on F, V acting on G, and last but not least, we can also have F times W acting on V acting on G. Okay. Just going to draw a line here to make it clear where the term ends and begins. Okay, and now we can start looking for some cancellations. So we have WF times VG here, and WF times VG here. We have VF times WG here, and VF times WG here. Now let's write what we have left. So VW, actually I'm going to put the G out front here. G times VW on F plus F times VW on G minus G times WV on F minus F times WV on G. Okay, so this is a little more clear for me now. Now we can group the F terms together. So let's grab F. We have the commutator of V and W acting on G, plus we have G times the commutator of V, W acting on F, and that is the Leibniz condition. So we've shown linearity and Leibniz now. Okay, so we can move on to part B now, where it asks us to let x, y, and z be smooth vector fields on a manifold M, and verify that their commutator satisfies the Jacobi identity, which is written on screen here. So let's just quickly run through this. It's just a boring computation. So we can just write out what they have. X, Y, Z, excuse how messy my writing is here, plus Y, Z, X, plus Z, X, comma, Y. And let me just remind myself what we're actually doing with this. We're going to, oh yeah, just verify that this satisfies the Jacobi identity. Okay, so we're just going to show that this is equal to 0. So let's go ahead and start expanding here. So this is xy minus yx z plus yz minus zy plus zx minus xzy. This equals xyz minus yxz minus zxy minus zyx plus, let's see, yzx minus zyx minus xyz minus xzy. And then just the last bracket to go, we get plus zxy minus xzy minus yzx minus yxz. So this xyz is going to cancel with this xyz. This minus yxz is going to cancel with this positive yxz. This negative zxy is going to cancel with this positive zxy. This positive zyx is going to cancel with this negative zyx. This positive yzx is going to cancel with this negative yzx right below it. And finally, this positive xzy cancels with this negative xzy, and we've shown that this equals 0, and in other words, that these x, y, z, which are smooth vector fields, do satisfy the Jacobi identity. Okay, now on to part C. So part C says let y1 to yn be smooth vector fields on an n-dimensional manifold M such that at each point P belonging to that manifold we form a basis of the tangent space Vp, and then at each point we may expand each commutator y alpha, y beta in this basis, thereby defining the functions C, which have this symmetry, and these functions C are defined in this way. So the commutator of y alpha, y beta is going to give us this C times y gamma. So it asks us to use the Jacobi identity, which is what we use in part B, to derive an equation which is satisfied by this C function, or not a function, the C constant, I guess, because they say, yes, this equation is a useful algebraic relation if the C are constants, and this will be the case, blah, blah, blah. Okay, so let's just go ahead and get started with this. So instead of writing this the way they suggest, I'm actually going to copy and bring this down. Oh, that won't work. Okay, let's just drag it down then. It doesn't like this. Here we go. Okay. So we can start with the Jacobi identity, but in terms of y's instead of x's and y's and z's, just to stick with the notation of the problem. Although what I'm going to do instead of using alphas and betas as the subscripts, I'm going to use x, y's, and z's just to keep myself organized here. So let's write the Jacobi identity like this. Let's say yx, yy, comma, yz, plus y, yz, yx, plus y, z, yx, y equals 0. So the question is, what can we do with this? And what we're going to use is this relation that they give us in the problem, where the commutator of the two y's gives us the C function times a new y. And there's an implied sum here. I'm going to use Einstein summation notation, so I'm not going to write the sum. But yeah, that means that we can go like this, and we can replace this commutator of yx, yy, with C xy down here, gamma, y gamma, times, or not times, with the commutator of yz, plus, and then we're going to do the same thing here. So replace this inner commutator with C gamma yz, y gamma, times the y, or not times, I keep saying that, comma yx, and then, yes, this last commutator is going to be czx, with the gamma upstairs, y gamma, times y, and this all still equals 0. Now, we're assuming that these c's are constants, because we're looking for this useful algebraic relation if the c are constants. So we're going to go ahead and pull these out of the commutator, because you're allowed to do that for constants. So this is going to be C gamma xy times the commutator of y gamma yz, plus C gamma yz, commutator of y gamma yx plus c gamma z x times the commutator of y gamma y y. Okay, and now we can use that same relation from the problem once more. So we're going to turn all these commutators into c's with y's as well. So that's going to look like this: c gamma xy times now c gamma z sigma y sigma plus c gamma yz. So again, we're making a new c, so we're going to have the gamma x down here and just give it some new index sigma again, times y sigma plus czx gamma c gamma y sigma y sigma equals 0. Now since this equals 0, we can cancel out, all of the y sigmas here. Then we get this relation with an implied sum over the c's. So this is c gamma xy, c sigma gamma z, or this sum over the gammas, plus c gamma yz, c sigma gamma x, plus c gamma zx, c sigma gamma y equals 0. And that is what we were expected to show, I'm pretty sure.